by our friend Karen Simmons. She is a longtime supporter of the CU Denver Physics Department. I thought I should mention that. She started out as a geologist and wound up working in space science for over 50 years. She started at LASP, the Laboratory for Atmospheric and Space Physics, in 1965. And so we have a nice history of our space program over all those years.
Okay, so the first thing I would like to say is that I just had to turn my hearing aids in because they weren't working. So if you have a question, say it very loud, or we're going to act as an interface here. So please go ahead and ask. Okay, so not this one. This one. Okay. No, that's the pointer. Okay, that's forward. There we go. Okay, so in 1965, I started working, can you hear me okay? There it is. Okay. With the rocket group. And the Laboratory for Atmospheric and Space Physics is a laboratory at the University of Colorado. And it was begun in 1948 when we had access to a couple of the captured V2 rockets from Germany. And what scientists at the university discovered was that nobody really knew a lot about the atmosphere of our own Earth. So we started flying, these Aerobee Rockets, that one. It's about 150 feet, and it's liquid fueled, and it flies to an atmosphere, into the atmosphere about 200 to 250 feet. It's a military rocket, and the research that we were doing was basically paid by the Naval Research Lab, the Air Force, and there's a third one I can't remember. But we flew these things about once a month. And what Fred is doing there...
Excuse me, this is banging against the microphone.
Oh, I wondered what... Okay. Well, Okay, that should help. This red object here is a ultraviolet spectrometer, and it's good at looking at the atmosphere and telling us what's in the atmosphere. Hydrogen, nitrogen, carbon, carbon dioxide. So we had these were developed in those early days of the 50s and early 60s, and they've been the workhorse of our research. This is the Mariner 71 spacecraft. It's the engineering model that we finally got a hold of after the Mars missions were finished. The Mariner spacecraft was again like a workhorse that NASA had developed, and they used this to fly to a lot of different missions. The first one that I was involved with went to Venus, and that was in, I can't remember. We used it twice. There's a package of instruments down here. And what NASA does generally on these spacecraft is they get a group of scientists who think they know about what the planets are like, because we had to depend upon astronomers in those days to tell us, well, it's bright and we think there ought to be methane, okay, or there ought to be carbon dioxide. And so there were generally around 10 different scientific instruments. The spectrometer, our spectrometer was in here. There's a wide angle and a narrow angle television camera, imaging camera. There's an infrared instrument, and there's a radio instrument that it's mounted on both ends of the solar panels. This is how we talk back with the Earth. And mounted in here on the inside are 3 different computers. One that controls the spacecraft, another that controls the instruments, and a third one that controls the communications between the science data and the Earth. So the first one that I was involved with full-time was the Mariner 9 Mars mission. There were 2 Mars missions that used that spacecraft that we just looked at, and one of them flew past and took data along this path, and the other one took data along this path. Now, this represents the size of the field of view. So the field of view would be aligned like this, and so in these 2 cases, we were much closer to the planet, so we got far more detail about the planet itself. But they were flybys, and so you only have a certain amount of time to take your data. This was the first data that we got from Mariner 6, which told us then what's in the atmosphere of Mars. So dominantly CO, CO2, hydrogen, we got a little bit of oxygen, and all of these are lines in the spectrometer at these wavelengths for different series of the CO2 bands. So that was the first information that we had about Mars and the atmosphere at Mars. But from the intensity, we could also tell that there wasn't a lot of it. But in 1971, NASA funded an orbiter for Mars, and so we got to Mars in 1971, and lo and behold, as soon as we got there, the first 100 orbits, we got very little data because there was a global dust storm going on. But once it cleared and we started getting data, this represent an individual orbit as we went down across the planet. Now, I guess I lost this, but it's about 60 degrees to minus 60 degrees. And so we were able to do a lot about what Mars was like. This is a spectrum from the spectrometer. Here's again the wavelengths. And this, whoops, keep doing that. This is a ratio of the spectrum at 57 degrees, this guy, and another one that was at 20 degrees north. And what we discovered was that this big deep dip in the spectrum represented ozone. So once we knew that there was ozone, we knew there must be water. And so we kept taking data. In many of those orbits, one of the first things that we did was we measured the atmosphere in all of those orbits. And what we were able to do was, this represents the size of our field of view here as we went over this giant volcano, which is called Olympus Mons. And by measuring the atmosphere, the reflectance of the atmosphere at this particular wavelength, we were able to see that there was very little reflectance here, but much more reflectance here. And so that meant that we were looking through more atmosphere here at a lower altitude than we were looking at here at a very high altitude. So we transferred that into an altitude topography map and published that. So here was some part of it. So Mars had these three north, middle, and south spot volcanoes, and then this tremendous Olympus Mons. 25 kilometers is 3 times the height of the highest.
Mount Everest.
Yes, thank you, on Earth. So it's big, it's big. So I wanted to put in here some data that's much more recent that one of the people in our lab worked on. Is the question of what's happened to Mars' atmosphere. When we were measuring the atmosphere here, we realized that we're not seeing very much of an atmosphere in Mars. So we were asking the question, what happened to it? And this research was done again by another mission with that same kind of spectrometer, and discovered that with the solar wind piling into Mars, the solar wind was blowing the atmosphere away. Well, why is it blowing away? It's blowing away because Mars's core is no longer presenting a magnetic field. And that magnetic field is part of what holds the atmosphere and deflects the incoming stream of particles from the sun. And so without that magnetic field at Mars, the solar wind is just blowing the atmosphere away. And so it's also connected to where the water went, because the water that would be in the atmosphere, and Clyde just gave me a great description of how that works, so you can ask him later on. I'm a geologist, remember? See, okay. Well, I want to go back here too for a second. Underneath this topomap, there are images of the surface of Mars. And right along here, and along with some of this topography that we measured here, this is what's called the Marina Canyon. It's 7 kilometers deep. And so because we had the volcanoes here, there was at least some indication that whatever the volcanoes were putting out, the lavas or something, must have been flowing down this channel. It wasn't until a little later that we figured out that what was flowing down that channel was water. And we figured that out by some of the very high-resolution images that we got from other locations on Mars. So that when you see a certain feature as a geologist, you know that water created that feature. Something flowing, mud, lava, most likely actual water. And there are plenty of places now that we see on Mars where we actually know that there was water flowing. And that's where one of the rovers is now looking for evidence of life in the deposits at the end of that river system. But all things come along, and we launched Voyager in 1977, and as we were approaching Jupiter, the Jet Propulsion Lab looks at images of objects and then fits those images to a known orientation of the spacecraft. And if that image doesn't fit the orientation of where we're flying the spacecraft, then we know there's something that's not right. And so it's either that the spacecraft is not on target or there's something else. And it was that image of, got it, I'll get this figured out yet. This image and this spot here said there's something unusual about this moon of Jupiter that we're looking at. And this turned out to be a volcano. So in the meantime, we'd been having some trouble with the hardware on our instrument. There are 3 wheels in the instrument that moves the spectrometer to different locations. There's another wheel that controls how big of a field of view we're using. We had 3 fields of view. And there's another wheel that was controlling polarimetry flights, filters. And Charlie had been out there. Charlie was my boss. And he'd been out there with the engineers trying to figure out, how do we fix this? And so Charlie, we hadn't gotten an answer. We were almost at Jupiter. Charlie was worn out. He was at the airport, and I get a telephone call. Where's Charlie? I said, well, he's at the airport. He's coming home. No, he can't come home. Tell Charlie to turn around and come back. So we had to find money for Charlie. We had to find clean clothes, and his wife brought a suitcase for clean clothes, and the boss got money, and we all took that and sent it to Charlie, because what we had seen, what was being seen, was this inner moon of Jupiter called Io. We looked at this picture, and we could not figure out what in the heck was going on. This is, compared to Mars, this was an amazing image of a moon. What is all of this? Well, I'm going to digress for a minute, because Jupiter was equally amazing. The red spot had been seen in telescopes on the Earth for several millennia. And the bands, these bands, there's different names for the dark ones versus the light ones. These are higher, these are lower in the atmosphere. But there's just all of these features. These are the white spots versus the red spots. This again is the red spot. You can see this tremendous amount of atmospheric turbulence in these close-up pictures. It turns out Jupiter's winds were blowing. I didn't look that one up. Something like 800 kilometers a second. When you consider the size of Jupiter, Jupiter is so big that you can put all of the planets and all of their moons and everything inside Jupiter. It's a huge, huge system. And so when it rotates, it just goes like heck. And produces a lot of this turbulence. So, we were just mind-boggled at what we were seeing. But we kept on taking data. We took a picture of what we knew was a ring. We didn't get much resolution on it. And the Cassini spacecraft later in 1983 or 4 took a much better picture at it. That's kind of a lesson that we learned after Cassini had come along. We were exploring. Voyager was exploration. And what we were looking for was trying to understand what are the planets, what are the moons, what do they have, what do they don't have, what do they like. And it was just an amazing experience and confusing. And a lot of the science teams were busy trying to understand a lot of this. When we got a little closer to Io, we began to recognize some of these features. This feature is a volcanic crater called Pele, and this is a cloud of sulfur that Pele is putting out when it erupts. And all of these other dots on here, these are lava lakes. This is an even closer image from Cassini. I'm sorry, not Cassini, Galileo, the Galileo spacecraft. So you can see these lava lakes. The lava pours out. Much of this cloud is a sulfur cloud. Gases are coming out of the volcanoes. There's something like 100 different active volcanoes on Io at this time. So more data to understand. This is an image of something that we were trying to do that on Voyager 1 we were not terribly successful at. So when the solar wind blows past Io, it starts to pick up these signatures of other gases. So the sulfur, several other constituents. The solar wind blows it downstream of Io as Io circulates around Jupiter, and what then forms within the magnetic field that Jupiter is putting out are these what are called tori. There's a ring around Jupiter that contains these atmospheric constituents that are being blown off of Io. And there is some material that's actually being blown off of Europa as well. This is one of the early pictures from Voyager 2 of Europa. Europa was a long way off from where we could see it with the flyby path of both Voyager 1 and Voyager 2. We got a little closer and we were able to see features like this, which to a geologist says that there's something flowing down the middle, and what's flowing down the middle creates these little humps as the material flows out away from the crack. And if you go to the deserts of southern Utah, you'll see on river channels coming down from some of the hills, you'll see these same structures on the sides of those rivulets. So we recognize that something was flowing up out of Europa when we saw these. When Galileo got to Jupiter, it's almost 10 years later, we started seeing lots more detail. But if you follow the cracks, you eventually see that some of the cracks then intercept or are cut off by other cracks. Here, in this case, there's a wide track, and it's been cut off by two other cracks that have formed. And so the scientists are saying, well, what's going on with Jupiter? We were pretty sure that this was an ice shell. Another one of the instruments could measure the water ice on the surface. But we didn't have any knowledge about how do we interpret what's going on here. And one of the geophysics guys came up with the answer. It's called tidal heating. So Jupiter is this huge mass, and it has these little moons flying around that also have mass. And so every time Jupiter is close to one of these, there's a little mass here pulling at Io. At the same time that there's a lot of mass at Jupiter pulling, and there's a little mass from Callisto and a little mass from Europa. So all of these bodies are busy pulling and tugging at each other. And because there's, what we now know, because there's water underneath that ice shield, that's helping create these cracks. There's the latest that's coming out of some of the science teams is that there's some indication that this might be similar to plate tectonics on the ice sheets, so that one ice sheet is going underneath the other, the same way that we see plate tectonics on the Earth. I'm not sure that I buy it yet, but we'll see more papers coming out soon. But this ended up being the real clue that guaranteed that what we were seeing here in all of this on Europa is that there's liquid water on this moon. There's a core, but there's no magnetic field. The next flyby was at Ganymede. Here's another indication of measurements that were made that there is water internally on Ganymede in several different layers. There's a core, and that these tidal actions apparently are what's moving all kinds of stuff around. Older surfaces, younger surfaces, perhaps liquid flowing up from one of these cores. And one of the instruments then measured this. These are aurora at Ganymede that tell us that there's a magnetic field at Ganymede. And that's important, because the magnetic field then helps protect the quote atmosphere of Ganymede. And this was a Galileo spacecraft measurement surface of Ganymede that says, yeah, old surface, younger surface, somehow some fracturing was going on here in one of these areas. And because there's some sort of liquid in here, salt water, pure water, something that allows the surfaces, the ice surfaces, to be moved around by these tidal forces. This is Callisto. Callisto is one of the oldest moons, full of craters everywhere. This is a picture from Galileo that shows that a lot of what's on the surface is very rough and is not being smoothed out by tidal forces that are acting on the other moons. So this is a very rough and very old surface. Now I'm going to throw this guy in here, which is not related to Jupiter's moon, but happened after we left Jupiter and on our way to Saturn with Voyager. We measured the comet Shoemaker-Levy. If you remember, that was the comet that broke up into lots of little pieces when it flew close to Jupiter, and as it came around again the second time, all the little pieces started hitting Jupiter. And one of the measurements that we made, this is one of the spots on southern area of Jupiter in the clouds that produce these dark rings and dense dark spot. And 3 or 4 of the instruments were able to point at those spots and determine the temperature and the particle sizes of the atmosphere of Jupiter. So it was a very successful happenstance that Shoemaker-Levy just happened to come by and break up just as we were on our way to Jupiter. So, Jupiter, or Saturn, sorry, rings. The rings are just plain unbelievable. They're very big, they're very bright. Our instrument took this observation, and it's all squished together here in this presentation. It's a false color geometry manipulated presentation of our data. And if you look real closely, right along up here, you see the F ring. It's really hard to see on here. But what we did was we took this narrow slit that we had and we put a star in the field of view of the slit. And we watched the star travel, travel, travel with the rings in between until the star went behind Jupiter. And what that did was it gave us the highest resolution of any of the observations, 2 kilometers of everything that was in this ring system. This is a picture from Galileo that I put here. You can vaguely see the pink color. It was something that started showing up on Voyager, but Galileo saw it also, and we still don't know why it was turning pink. But we did a lot of work on the rings, because nobody really knew what the rings were all about. A lot of papers came out, a lot of work was done, and I'm just trying to present a small part of what we did learn. There are lots of gaps in the rings, and you can see quite a few of them. and what's called the Cassini gap, which is this dark gap right here. So we've got a D, C, a B, and an A ring, and then this tiny F ring out here. So this Cassini gap is controlled by what's called a 2-to-1 resonance with this moon, Mimas. And so the rings go around twice for every time Mimas in its orbit goes around Jupiter. And each time Mimas passes the same location, it gives a little tug on those particles in this location. And eventually what it does is it moves all of those particles outward toward Mimas. The same thing happens with all of these other particles that are in different places in the rings. So there's now 147 moons of Saturn. And almost all of those, beside the very big ones, they're almost all in the rings, doing the job of creating all of these dark areas in the ring system. But what we did see later on, the Cassini spacecraft, which came after Galileo, it took a real close look at the difference between the D ring, right down here inside, and how it had changed between Voyager in 1970s and Cassini in the late, let's see, this would have been, I think, the late 80s. But you can see here that something has moved in to clear out this ring here. This ring is still there. So there must, a particle may have moved in to clean out this ring. And so this is one of the fun things that we started seeing between an orbiter, which can pick up lots more data going past these objects time and time and time again, versus with Voyager, when all we were doing was flying by, and we could see some good stuff, but we couldn't see everything that these orbiters are now picking up. And Galileo is the same. We then went, well, let's see. The first thing is that I'd like to show you at least a couple of these bigger moons. So here's some of the, we did an extensive amount of work on the cloud systems. And it's good science, but it's probably not one thing that you want to see. So here's Titan. Titan, we expected to see great stuff. And this is all we saw of Titan, is this methane cloud. And when we're looking at the limb, we were able to see a little bit past the cloud, but not by much. So we had to wait for Cassini to come. Cassini was the one who discovered all these 147 different moons. And what it also did was identify a lot of these features on Io. So on Io, we have what are called lava lakes that were these dark spots, but they're not the same as these dark spots that are called Mare, that are geologic dark reflectant surfaces, probably lava, cold lava. There were also clouds. We're also seeing some clouds, most likely sulfur clouds from the eruption of some of these craters. This is, we're going to get over here to Enceladus too, but here's a sort of a panorama of the bigger moons of Saturn. Here's Titan. Titan was really surprising because on Cassini, their spectrometer had more wavelengths, and they could see many more of the constituent features than we could with the Voyager instrument. And so there's some great pictures from all of these guys. And I'll tell you how to find those great pictures at the end here. But this was the big surprise at Saturn with Cassini. Cassini identified that there was gas, I'll say gas, escaping from Enceladus. So here's Enceladus. It just looked like a white ball to us. But lots of activity on the surface. Again, that pretty much starts to hint that there's motion underneath the ice crusts. And Cassini was able to fly by so close that it could measure what this gas was. And it's water. It's water. And, yeah, question?
Just curious, when I was a kid, just for reference sake, there were 9 planets and 31 moons, but anyway, that's irrelevant. When I was a kid as well, they said that...
Can you give him the...
Oh, I can yell.
I'm sorry. As I said, I had to turn in my hearing aids because they weren't working.
No, I just had to laugh with the 147 moons because there were 31 when I was a kid. My question is actually, do they have a theory, and maybe you're going to discuss it, as to where the rings came from?
Hold it a little further away from your mouth.
Is there a theory as to what formed the rings? Because when I was a kid, they said it was a moon that got too close and exploded, and that formed the rings. But that seems to be discounted today.
Okay, I think I've only got the latter part of that. Can somebody translate for me?
What makes up the rings?
Where did the rings come from?
Okay, thank you. Thank you. I did all of this chaos with my hearing aids. The ring particles are mostly ice. This F ring that we were looking at, that's way out here on the outer edge, is about the size of a VW bus. And as near as we can tell, and especially from things like these observations, that they're ice-covered particles, probably from interactions, collisions of incoming comets or asteroids, and collisions between particles in the rings themselves. So some of the particles are slightly bigger than other particles, and as they collide going around, they too produce more material. And so the theories from even astronomy centuries ago was that this material is probably making its way eventually to Saturn, and will eventually end up in Saturn after some amount of time. How long it takes? Well, here's one indication. This is a period of 20, 30 years. So it may not take as long as we thought, but we don't know. I don't know whether the Cassini people have actually gone back to look at their data to see if they have seen some other comet or a larger body come flying in comets would be a typical source because they would be moving and they would be entering the ring system. The ring system is very, very narrow. It's only about 10 kilometers thick. And so it doesn't take much of a body to knock parts of it out of their current location. Thank you for the question. Enceladus, water. As Voyager aged, Voyager was a mission to discover the planets, the moons, the atmospheres. Eventually, when we started seeing all of these bodies with ice and clearly with water, NASA began to make missions where the object was the search for life. And so there was, at the moment, there's a new mission called Juno at Jupiter, which is studying these magnetic fields of Ganymede and what is the effect on the core and the ice. This is a lot of ice also, and all of these moons, except for a few, are just covered in ice, and most of them is water or CO2, and it probably comes from asteroids delivering water from other places and flying into these bodies and leaving water behind. A new paper just came out like 2 months ago. We've been studying our own moon and trying to decide whether there's ice on the poles on the moon. And one of the guys who has worked on Voyager and Cassini, they're looking at the dark craters that are in the shadow. If the sun is in this direction and the sun never hits this part, any asteroid that hits this likely will deposit water, and that water will stay there until the sun either shines on it, which is not likely, or something else happens to the water. But they're now saying that this is why they think there's actually water at the poles on the moon. And so we'll see later on that some of that Lyman alpha observations in conjunction with a couple of new missions is a reason why there's now a lot of information about where the water came from, not only on these bodies, but on the Earth as well. Okay, so that's Enceladus, and this was just mind-boggling. Water. But Voyager did not stop. Voyager just kept going. And Voyager 1, originally, the Voyager mission was called the Mariner mission, and it was only to go to Jupiter and Saturn. And once we started finding all of this, NASA decided that it could send one of the two spacecraft on to look at Uranus and Neptune, and the other spacecraft could go out of the plan of the ecliptic and into outer space. And so this is saying goodbye to Voyager 1. Voyager 1 then All of these were flying in the plane of the ecliptic. Voyager 1 then took a swing past Jupiter to change its orbit and move it out of the plane of ecliptic and eventually to go into the heliosphere and beyond. But Voyager 2 kept going on, and at Uranus, this was a huge disappointment. We couldn't see anything. We couldn't see underneath the cloud. It was sort of like looking at Titan all over again. We knew there was methane, but that's all that we knew. But what we did find was we found a magnetic field. And it had rings, so we measured the rings with that same stellar occultation method. And we could tell from some of the moons that this magnetic field was playing an act in reorienting some of the materials on some of the moons. Titania is further out. Oh, I'm sorry, wrong planet. It's further out. This body, Miranda, is pretty close to Uranus, and so it should have gravitational pull from Uranus. And so again, we suspect that how clean this surface is of craters compared to this older surface. Look at all the craters over here. This surface has been manipulated, probably by some gravity pull of Uranus, and most likely from some water material underneath in the body itself. But Titania is much further out and is apparently not getting that same pull. So here's the lineup of Uranus's moons. Here's Titania. It's big. It's further out. Here's Miranda. It's quite close to Uranus, and it's small. And so all of this operation, newer surface, very old surface, is probably due to a gravity pull by Uranus. This is Titania again, much further out. Probably doesn't have water. Probably. Don't know. Voyager will be the only people who see it for a long time. But there's a project being assembled to send an orbiter to Uranus and find out whether there's water in these guys. This one has some bright spots that could show us that. These two, now this one, hard to see. Again, this was flyby from Voyager, and so the moons were a long way away. And so we concentrated on something that was closer to Uranus that we could see as we were flying by. But we kind of see either giant craters or maybe volcanic action on Oberon. So again, this is now becoming the search for life elsewhere. And so Uranus is the next target. And, well, it's going to take a long time to get there from the Earth. It'll probably be close to 10 years to get there. And so if they launch it in 3 or 4 years, I might see it. Neptune was a little more kind to us. We were able to at least see some clouds on its surface. This is Triton, and the ice here on Triton is the coldest surface in any of the bodies that we've seen. Of course, this was before we went to Pluto. Pluto's got one heck of a ice surface. Rings, we got more ring pictures. So this body is gravitationally attracting moonlets. And this little moon we spotted, it doesn't even have a name. It's just 1989 and Neptune. So one of the other things that we have been doing, we launched in 1977. We got to Jupiter in 81. And in that first period, we looked at the Earth, we looked back at the Earth. Carl Sagan wrote a paper saying, yeah, there's probably people on the Earth. And we looked at the moon, and we flew around Venus for gravity assist. And so we got some more Venus data. But in between all of these other things that we were doing, another one of our science team was making measurements of the Lyman alpha heliosphere. And this is the Lyman alpha, what is that acronym? Interplanetary medium Lyman alpha. So this is the Lyman alpha that's out in that area that we were talking about, where the solar particles will come in at us. The alphane magnetic protection that those alphane rings provide pushes those particles away from us. And you can correct me if I got it wrong, Clyde. But it tells us what's out there in the heliosphere where the planets are not at. And hydrogen, is one of these key ingredients, because with oxygen it makes water. Helium is, well, now you really will have to help me, but I think helium is one of the first things that comes out of the, I've forgotten the name. Sorry, I'm getting old. But so I wanted to come back here and say that these measurements of the hydrogen from Voyager 1 and 2 help us understand that Shoemaker-Levy comet that came flying in and ended up hitting Jupiter. That comet was bringing hydrogen with it. And it's been as part of that same observation where they're looking now at the water in these dark craters on some of the planets and at the moon, because hydrogen with the oxygen is making the water. And so knowing how much hydrogen is out there is key to understanding where the water is. 50 years is a long time to try to remember everything. So excuse me. We'll just say, here's what Voyager is starting to see after it left this heliopause, which is that area outside of where the planets are, but before you get to interstellar space. And so once Voyager 1 got to interstellar space, so it's no longer in what we call the solar system. This is what it's been seeing. And these bright spots are like those CMEs that we've been seeing. It's plasma. It's the plasma, and it's the plasma that the sun is putting out, and it's moving out into space. And so we probably wouldn't have guessed, I certainly wouldn't have, but the astronomers probably had speculated that plasma is going out into space, and it's probably hitting all of those other bodies that are out there that we're not aware of yet. You know, we're starting to see lots of other planets, but they're a long way away. But Voyager left. Bye. So that's it. That's the end.
Did you want to take questions?
Now,
Do you want to take questions?
yeah, we can take questions. I'll do my best to hear.
Okay, so please wait for the microphone. So you say you had one right here?
What was the favorite thing that you studied over the course of your career?
Oh. Well, as a geologist, the moons were just fabulous. Io was the first surprise. What we're seeing on some of the moons with this interaction with how much water is apparently in the body that's creating faults, resurfacing, building mountains, tall mountains. These are like 20 kilometers high. You know, they're easily what we would see on the Earth. And the different shapes. So there's no erosion like there is on Earth. And so just looking at these bodies, water on Mars is probably, because Mars was my first child. And it's clear that there's water there. It's not clear whether they'll find evidence for life, but it's absolutely clear that there was water on the surface of Mars. There's likely ice under the surface, but whether there's the same amount that we might know that would be similar to Earth, it's probably not that much. Yeah, it's been mind-boggling, it has to say. Yeah.
Why didn't they keep Voyager 1 in the plane of the ecliptic?
Well, this is harder for me to hear.
Why didn't they keep Voyager 1 in the plane of the ecliptic?
What kept it there was the navigation team. So on one of those spacecraft computers, they pick up data from what are called solar sensors that are mounted around the spacecraft. And then they triangulate with those known stars to adjust the spacecraft orientation to keep it going where they want it to go. And they have little thrusters, which are starting to wear out, be problems. But it keeps it in the plane of the ecliptic because that's where the planets are. Does that answer it?
I thought you said they didn't stay in the plane of the ecliptic with Voyager 1.
Oh, Voyager 1 then goes out of the plane because it was going to be the shortest distance to go up, out along the North Pole to get to the heliopause. And so that would be the shortest distance. And because it was in orbit around Jupiter, it could get a great big boost by flying very close to Jupiter and get a gravitational push to get out of the plane of the ecliptic. Thank you. I'm sorry, this hearing aid problem is terrible.
You said, is this close enough? You said that the presence of an ozone told you all that there had been water on Mars. So why does an ozone indicate that there had been water?
Okay, so I'm going to come. The microphone is just pretty much confusing me. So tell me.
So why does the presence of an ozone on Mars indicate there had been water?
Because ozone is formed from hydrogen and oxygen. Ozone is O3, so mostly oxygen. And the question was, why was finding ozone important? And that's because it tells us that there was enough oxygen at some time to form ozone. And ozone is oxygen 3, and we have it in our own atmosphere. And because it will freeze, ozone will freeze to make ice in those CO2 and oxygen water layers in the poles of Mars. And so knowing that there was enough oxygen to make ozone means that likely water, because it would then combine, then it breaks off one of its O3s and forms with the Lyman alpha, the hydrogen, and forms water. And so that was another point at saying is likely water. Thank you.
I have a question.
Come,
So,
yes.
do you think there should be such a focus on a manned mission to Mars, or would the resources be better spent sending unmanned resources to Mars to look around? What do you think about that?
Well, you're asking a geologist who bangs on rocks. There are certain things that man's eyes will see that an instrument won't. That was definitely true when we were first making these spacecraft. So the Mariner spacecraft was created in the early 70s. And if you think back, I mean, we were using a old-fashioned tape recorder to record our data. Inside that spacecraft, there was a recorder that had real magnetic tape. And if we were not able to send all of the data to the ground at the time, we just recorded on the tape recorder, and then play it back when we started having manned missions. We did not have access to the big antennas because they had to be used to watch the men in space. And so stuff got written on the tape recorder. But it's a tape recorder. It's got mag tape on it. And think back to the early 70s, our detectors were photomultiplier tubes. They're all digital detectors now. But we were working with what we might call the dentist's early tools, open wide. And so it's amazing what the engineers were able to do. The computers were all 8-bit computers, and so all of the commands that we gave to the instruments were octal commands, octal 8-bit commands, and those were sent to the onboard the communication computer, which was a 12-bit machine, and those were then loaded up to the hard core of our instrument. There were no microprocessors in the early days. It was all electronic, wired into. And one of the interesting side events was that one of our engineering monitors stopped working. And we finally figured out which one it was and where it was. And the engineers at Jet Propulsion Lab decided it was a cold solder joint that was the problem. And they were able to feed enough power through the system to heat that location and resolder that connection. And so, we now hear about the engineers working on Voyager, trying to figure out why Voyager stopped talking to them. These are really clever engineers. And actually, there's a good YouTube description of what they've been doing. And the young man that's giving it actually worked for me on Voyager in the 70s. It's like who we talk to that have been our students. There's 147 moons of Saturn now. And I was thinking about it the other night, and I think I probably had at least 100 different undergraduate students that worked for me over the years. And they're all out there someplace doing space stuff with NASA and other companies. It's been quite a path, quite a path. Yes? No, I'm just going to come over. There's something about it's probably the phone cover that I don't hear so well, so ask me.
If you were the president of space exploration, what would be your priorities over the next 20 years?
Well, they're planning on this Uranus mission, but I think they're going to have to think really hard about whether they want to spend the money instead to go pick up these samples on Mars. I have my questions about whether those samples will actually have fossils or any other indications of life on Mars, because they can't drill very far down to get that sample. But whatever it tells us, I think is probably where I would say that's the next thing. The other competition is coming from sorry, my memory doesn't work as well as my hearing aids do. The electromagnetic problems that we have with solar bursts and our electric and electronic systems now on Earth. There's a lot that we really don't know about the sun and why and how the sun produces these sunspots and decides to throw out these coronal mass injections, and where do they go, and how do we understand them more to know whether this one that's coming might kill our electric system, whereas the one that came last week didn't seem to have any energy enough to do anything. We barely saw an aurora out of it. And so that's a threat. And so there are many different places where it's like all of our government, you know, where to spend the money, what has. But as a geologist, I would like to see what those samples say. But clearly, I'm prejudiced. I've put badges and some other material on the table. In the early days, NASA used to give us printouts and slides, and every mission had its badges and our hats and our T-shirts, and much of that doesn't happen anymore. It's almost all digital. But if you want to know more, I would highly recommend you watch the NOVA Solar System series. They happen every Wednesday on Channel 6 at 8 o'clock, and they're fabulous. I mean, there's all this new information that, geez, I'm learning all kinds of stuff from it too. It's fabulous, and they do a great job. They barely ever mention Voyager, but sometimes they do.
Sorry, just one quick clarification. Are those badges just for display?
Yes,
Okay,
yeah.
so don't take the badges.
No. Anything else? This was fun. It really made me think about what went on in 50 years of my life. Wow. Another question here? Uh-huh.
So in the past, they thought water was really rare, say, in the solar system.
Yeah.
Now, they're saying, well, Europa has an ocean, Enceladus has an ocean, and Mars has an ocean underneath it, and Earth has another ocean underneath the ocean. So all these different.
Yeah, and there's one of the moons, and you know I've looked at so many moons in the last couple of weeks. One of the moons has more water than all of the water in the rest of the solar system, including the water on Earth.
Well, what moon?
I don't remember.
But how come they're saying all this stuff now when they didn't before?
Well, you know, because this is all new information, and we really had no idea that there was going to be that much water anywhere else. We had this inkling on Mars, but we thought the water on Mars had all been evaporated, except for some that might have been buried under the surface, or that is currently in one or two of the poles. But it's a small amount of water compared to what's on the Earth, for example. But this other moon, and Google it. I'm sorry, I can't remember. It's a tremendous amount of water, and it's just, you know, how can this be? But for example, if there's a collision with that moon from an asteroid, for example, that asteroid itself has got water from the another word that just disappeared. But the asteroid has water, and if it creates a crater on this moon that then blows up information, some of that water may then drift along more and fall on some of the other moons. Because what we're seeing on almost every surface is ice. And it's either CO2 ice or it's water ice. And it's everywhere. And it's far more water than anybody had speculated about. And it's, why isn't there more life? Is there microbial life? What do we want to know? What do we want to know? It's the question you asked. It's one of the reasons why I would say I want to see what they found on Mars, because it could tell us that at one time, before all of the surface water disappeared, that there were definitely lakes, there are these canyons, and there's lots of river features on Mars, but there's no water in it right now. But sometime in the past, there very well could have been. And so we pretty much know why there isn't at this point, because all the water has, at least the surface water has all disappeared. It's been evaporated off. But there may have been, and that would be a hint about how life began on Earth then. And because we still have an atmosphere, we still have water. There's just lots of questions to be answered. Yeah.
There's a mission called Europa Clipper that's
Yes.
supposed to have launched?
Yes.
Did it just launch?
No, it was delayed,
Okay.
but yeah, it will take a couple of years to get there. Again, it's out there at Jupiter. It took us from 77 to 81 to get to Jupiter, and we had to go around. We went around Venus once, and then we went around the Earth twice to get gravity assists to give us enough energy to get out to Jupiter. And so it'll take the Clipper that much time as well. The Voyagers had names, come on, brain, radioactive heat source. They were 2 canisters, and they were in a device that then the heat would create electricity. We don't launch that kind of power source anymore. It's a little bit too dangerous to try to launch plutonium on a spacecraft. And so there's different kinds of, there's the ion push. You put up a big screen, and the ions coming from the sun pushes against that sheet and drives a spacecraft on. In the early days, and Jupiter is going to be one of these too, solar panels work at Jupiter. You're close enough to the sun to get power from the sun. If you're going to Uranus, that's not going to work. It doesn't, no, not going to work. I don't know what the Clipper has. I haven't had time to follow it that closely. But yeah, it's going to be exciting too. Yeah, yeah. Yeah, just a lot of stuff going on. So, thank you. Thank you all. Thank you for helping me remember 50 years of my life. Okay, let's see. Yeah, turn me off here.